Today we're going to talk about a paper called PatchMatch. Uh, so, so, so I'll just discuss the key ideas proposed in this paper, and I'll show the implementation and applications. One of it is stereo imaging, like where you can reconstruct the depth from two views, and the other one is inpainting, and and I'll then talk about image retargeting and some other applications. Um, so so basically, why do we care about extending what we learned in the last class? So why do we care about matching patches? Because yeah, so this is the paper. It's been cited like tons of times. So why do we care about matching? So what this paper proposes to do is basically when you're given two images, you have to match every pixel to every pixel in the corresponding image. Two images of the same object, of course. So why do we care about this? It can be useful in many things, like for example, last class we saw that by matching patches between matching similar patches between images within the image can lead to can give us denoising, which is basically non-local means. And we took it to an extreme, and we also talked about bilateral filter, where you match every pixel instead of the patches, right? So added to that, by knowing if you're given two images and if you know which pixel corresponds to what in the other image, you can reconstruct and you know how they are acquired. Then you can reconstruct the depth from where you're acquiring to what you're acquiring. So, and then they can also be used in retargeting. Retargeting is, I think, it was also mentioned in the lecture. When I'll show you an example later. Inpainting and many more. So what did we learn before? So we saw naive search, right? We basically we saw like whenever we want to match patches, you can just choose a surrounding box, and you can match every patch in this box, saying that okay, if it's similar to me, then I'll give it a high weight according to the distance it is away from. And we saw that in bilateral filter, you can also match this pixels according to the intensity value. If it's of low intensity, I won't give any weight. If it's of high intensity, if it's of similar intensity, then you give high weights, right? So for every pixel you do this, and you basically try to find some non-local average of this and replace it. So we saw that it gives a denoising. So what is the problem? You have to search too many patches to find a good denoiser. So what did we see beyond that is when you can actually take these patches, compress them using PCA, and just decrease the dimensions and reduce your search space, right? So basically you get a small to get to go to a pixel, define a small neighborhood, and look for these neighborhoods around the images. But instead of looking for this whole neighborhood, you just decrease the number of dimensions by significant amount, and you saw that it can lead to even better results uh, than matching the whole thing, because noise is contained in the rest of the eigenvectors, right? So yeah, if we talk about complexities, first in the first algorithm, if you say capital N is the uh, number of uh, number of pixels in the image, you have to basically go to every pixel in the image, and you have to replace it. You do M operations at every pixel. In K, you basically decrease by an order, but not anything. You just decrease by a scale. It is just scale, but it's not decreased by any order, right? So now, in PatchMatch proposes the following interesting ideas. So what it says is, instead of matching the patches, you just match the offsets of the patches. I'll explain what it means in a couple of minutes. And it also talks about the following assumption that okay, if my patch is somewhere close to the if I have a corresponding patch in a certain position, there is since our objects are pretty piecewise continuous, or whatever you call it, so I mean it's pretty ordered, so they also correspond to the next pixel will also correspond to the patch which is closer to the corresponding patch. This is the major assumption. So and then so I'll probably come back to this slide after explaining the algorithm. So first, the algorithm goes as follows. So for every pixel, uh, you initialize a random so what they call it as a random field, nearest neighbor random field. What does it mean is you go to every pixel, you assign some random pixel in the other image, which is corresponding to you. You don't care which one, you just assign something, right? And you assign this for all the pixels in the image. So that's what is your initialization here. Let's say these three are the patches here are misleading, but for every pixel you look at the patch and you and you map another pixel, but you also look at when you're matching when you okay. Let me start again. So you go to every pixel, you go to another pixel, you have a random field which is directed to another pixel in the another image, and then you match it. I'll explain where the distance comes and why the patches come here. Let's assume right now that these are pixels, right? So and then once you assign all the pixels, then you want to propagate. You want to check what is the distance, which pixels are matched correctly, and you want to propagate that. And by propagating, I mean you're forcing the next pixel in the image to be mapped to the next pixel in the corresponding patch, right? So, and then after propagating, you just do some random search. I'll explain better now. So, here you're given as an initialization. I want to use my mouse. So let's say this is your image. This every pixel is mapping to some random pixel in this image, and so on. Like every pixel in the first image is mapped to is given a random offset. Is what by mapping I call it a random offset. So you have this random field where where these pixels are mapped to another in a random way. So then what the propagation means is when you take so you take you check the what you call as a distance. So this distance is basically captured by looking at the surrounding patch. When so you go to the pixel in the first image and then look at the patch around it and then calculate the patch around it in the other image and see how close they are. So if they are close, then you propagate the next pixel according to the distance, right? Is it clear, or I want to repeat it, or I can draw also? Because this is the only thing that is important. So if this is so you have an image like this. You have your source and a target, right? So first, I want to map each pixel in this to a random pixel, right? This gets mapped here, this gets mapped here. Okay. Now you go to this pixel and define what is called a neighborhood, which is the patch. So this is my patch, right? Let's say these are zeros for now. I should have started from here, but okay. So and then you calculate the distance between this patch and where is it mapped to? This patch. So so you have for every pixel you have a random offset, and you also have a distance to this patch. Let's call it dist. So for every pixel you have only 3 numbers, right? Doesn't matter. I mean, there are some distances that they define, but let's say L2, right? You can also take the Gaussian take Euclidean Gaussian kernel and then calculate the distance. There are some things that you need to use, but this is just details. So for every pixel you just have 3 numbers, and then this is the initialization step, right? What happens in propagation step is then let's say this point is okay. So let's say my distance for this pixel is by distance I mean the patch and this patch and this patch. For this pixel it is this patch. So let's say this distance is smaller than this distance, right? So what do you say is okay, then since this is smaller, then I'll just align my pixel to this one. So I mean, you don't just see this. You don't just see this one. You also see the pixel next to pixel right to it and pixel bottom to it, and then you do it for everything. So initially it was assigned to all random neighbors. now slowly the information is propagating that they slowly get assigned to the correct neighbors, right? So this is the propagation step. And then once this is over, then you take then basically you just choose you choose a random then you go to every pixel in the image, and then you see, okay, let me check from randomly in the space. I'll just take a random guess and check this patch if it's closer or not, and you do it at an exponentially decreasing time. Let's say you do it for r by r, then you decrease your search space by r by 2 and r by 2. Basically, you come down in like until you reach a pixel size, which means let's say if the whole image is 90, you just come down in 6 times. So basically, you do 6 searches, and just so that you can refine your you can refine your guess, and then you do the whole process again. Is it clear? Which part is not clear? The last one. So you have so once you propagate the information, then you take a random window of big size. Let's say if your image is 150 by 150, then just take 150. Okay, and then you search through. Then you take a random patch from this whole image, and you see if the distance is smaller or not, right? From this pixel, from the patch of this pixel, right? When this pixel, I mean this one. So you see this distance and this distance, and then since if it's not smaller, then you kind of decrease it. So then you make it 75. Then you search in a 75 by 75 window, and you see if you get a random patch from this, and then match it if it's same or not. I mean, not necessarily here; it can be anywhere. And then you do it, next time you do it in a 37 by 37 window, and so on. So basically, you just it's just since the algorithm is random, so these guesses might refine its initial guess to something else, and then you repeat the whole process again. Like you again estimate the neighbors, and then again do the random search, and so on. Okay. Maybe it'll be clear when I show the code. So this is it. So why should such a thing work? So let's say my pixel has my whole image has m pixels, right? So this has like 150 square pixels. So what is the probability of getting the correct guess? It's 1 by 150 square, right? 1 by 1. Let's say if I call it m, then it's 1 by m, the probability of getting it right. But the probability of getting it wrong is 1 minus 1 by m, right? So what is the probability of getting all the things wrong? Is 1 by 1 minus 1 by m to the power m, right? So even if you do one thing right, which is, I mean, for a normal sized image, I think 4 MP or something, it's 0.37, right? So at least there's a 60% chance that you get at least one thing right. So if you get one thing right, the information gets propagated because you're looking at the neighbors. So slowly all the random fields get aligned, and it will be able to actually align itself to a correct to pixel wise mapping with a high probability. If you increase, I mean, if you get only one correct guess, then it's this much. If you have multiple correct guesses, if you're lucky, then you have even higher probability of converging. So this and it works really well. C is the number of correct guesses you get in the first chance. Let's say you have only one correct guess, then 1 minus 1 by m, right? If you have C correct guesses, then 1 minus C by m is the probability of getting C correct guesses. Yeah. So let's now so now we'll see how to code this, and I'll specifically talk about two applications. One is stereo estimation in stereo depth. I mean, you want depth estimation in stereo acquisition. So what happens in a stereo acquisition is the one you see on the right. so you have two cameras with a limited distance between them, and both of them are acquiring the same scene, right? So you have a little shift between between the cameras, and this can be used if you use this with I mean, and you know the D, right? The D is how your camera setup was established, and that is also called as the baseline of the camera. So if you have D, and if you have which pixel maps to what in the other image, you can actually reconstruct what happens in actually reconstruct the depth, which is this thing. You can actually reconstruct this if you have this and this. I mean, corresponding ones for the same pixels. So, we'll not obviously estimate the depth, but we'll find the correct neighbors for images taken with different views. So, estimating the depth is just geometric multiplication. So, let's see. It's nothing. It's just implementing what we talked right now. So let's start. Sorry for the Jupyter. I wrote it. So actually, why do I have to run it? I already have it. So I'll just first go through the code, and then I already generated all the results, so you can run the same thing. Because it takes like actually this algorithm runs in real time, but I have a bad implementation, so it doesn't run in real time. So you can also I run for more iterations. So let's see how to start this. So NNF is a class I define, and when I define a class with giving it the inputs, it goes to the init, and it basically initializes both the NNF is my random offsets, and NNFD is the distance. So distance, a random offset should be where this point is mapping to that point, right? So it's 2 times the image or image size, and distance is basically the distance between these 2 points. So first I'm defining the image size and image the other image, and I'm defining the box size as what am I giving, 7, yeah. No, I'm giving it as 3. That's why it's 7. Yeah. So, and then I'm initializing this random offset and this distance, and then I go to init and nf. So at every in the first point, I'm just generating random integers, which is of size this matrix, and I'm putting it in O and nf of O, and then and the same thing for even 1. So and then at every point, then you go to every point here, and then you want to look at the patch around, and then you want to look at the patch around here, and you calculate the distance. That's what is happening here. So calculate distance is I think it's L2. Yeah, it's L2. I mean normalized L2 norm. Yeah. So and then so this is when I initialize it. Then I ask to nnf.solve, which is basically propagate plus random search. So it goes to improve NNF, and improve NNF calls. So total iterations, I'm running the whole thing for 5 times. In the paper, they suggested that it should, I mean, with high probability, it should converge in even less than 5 times. So for each iteration, I'm going to every pixel and then looking at the initialized random offset, and I'm going to see what pixel is next to it, what pixel is above it. And in the paper, they also suggest that in even iterations, they ask you to look at these, and in odd iterations, you have to look, they suggest to look at this and this. It doesn't matter. It just I mean, if you do both, then it doesn't matter. So so you look at that, and then if the distance is better than that, you just assign this to the current pixel and map it accordingly, right? So this is it, and then random search. So rand D is basically this window that I'm defining. So so I define it to be I mean, you can always change it, but I'm defining it to be half the size of the image. So if I change it, then if the patterns are pretty non-local, then there's some chance that it might find offset which is far away, right? And then I do it, and then I I just decrease it every. I just search for pixels and then I decrease it every half, right? So at the end, I get an NF of every point, basically how this point is mapped to the pixel in that point, and the distance corresponding to it. We're not interested in the distance anymore. After we finish it, we're just interested in where it is mapped to what. We can always calculate the distance. Distance is just a criteria when we're programming it. So so the problem. Wait. So okay, so this is this is the stereoscopic reconstruction setting. Basically, this is image acquired from one view, and this is image acquired from the other view. The camera is like this, and the baseline is known. So I'm trying to estimate. I'm trying to estimate this view. Wait. Yeah. So I'm trying to estimate the view 1 from view 5, right? So I want to, so view 5 is my, so I want to reconstruct view 1 from view 5, right? So I will use only information available in view 5 and just put all the pixels there and visualize what I get, right? So is it clear what is happening? So view 5 is so if you see, it is doing a pretty good job. Wait, I think it's the opposite. So I'm trying to reconstruct view 1. So okay, and I'm using all the information in view 5. Okay, that's fine. So so if you see these both images, you see that some pixels are never seen in view 1. So obviously it can't put it anywhere there. So it just puts from random pixels. But most of the image is perfectly recovered, which means that it basically recovered a very dense correspondence between similar pixels from different views. So basically, when you have a lot of dense correspondences, you can obviously estimate the depth to every pixel. Assume that for every pixel you can estimate the depth, right? And basically, your depth is not so accurate in the portions where it is not predicting properly, and the other places you can. So, but so this is one, and also for the other, the same thing, right? So I'm just trying to reconstruct the view 1 from view 5. So I mean, one thing to notice is I just decreased the size by 2, so I can run the algorithm fast. So don't mind the blur, but other things are estimated pretty clearly. So so you can also use this for semantic inpainting. What is semantic inpainting? I will cover some. So let's say I have this image and I cover this part with the black thing, right? And I want to estimate what this is. I want to look at the other image and just put whatever is held in here. But so how do you do it? So I just give this inpainted image as a target, and I know the source, and this source basically puts everything here. So puts every pixel from here to there. Since you have perfect correspondence, and this correspondence is flowing very effectively, you are able to reconstruct this. So this third one is an estimated one, and the one which is shorter is the estimated one. Basically, this view one edited is where I painted this black thing, and view 1 is the original one, how it should look like, and view 1 edited from view 1 whatever is the reconstructed, right? It's pretty good because see what is happening there. Basically, it just estimated some good estimate of it basically got some good estimate of this, and it's just propagating in this direction, which is really cool because that's what it's supposed to do. Yeah. So and then the same thing, I'm just cutting this information off, and it's able to recover this patch by looking at the corresponding neighbors from neighboring pixels from this and this, right? So which is so it can be actually this operation what we saw right now, it's used as some brush in Photoshop. It exactly runs PatchMatch and just propagates the information through this way. So it's at least in CS6 it was using that before deep learning. Now I don't know. So and then you can also do the following thing. You can just mark which places are important for you and which places are not, like in Photoshop. And you can, so basically along these lines it propagates the information. It says that okay, these lines are alike, so you can just look at the patches or pixels within these lines and reconstruct, and so it's able to basically remove this bird from where it is. So you can do this, they call it like guidance driven inpainting. So yeah, so what is a good thing about this is now you're reducing your search space by a lot, because you're just searching along these lines and not at other places. So you can just, it just replicates everything, and then it for the background it just propagates information from the surrounding pixels, right? So yeah, this is we'll talk about retargeting for some time, and that's it. So retargeting is basically when you have let's say when you generate some the problem originated in 2005, when many devices were popping up, like mobile phones, tablets, and the web computers, whatever. So when you have an image, you have to see it in a good view from all these devices, right? So you have to scale them appropriately and not scale them so that information gets jammed some places, and it's where it's not important. And for example, here you don't care about how much grass is there on the ground, you care about the person and the building. So that's why it's good to remove this and put the person and the building alike, right? When you want to look at it on a web browser, you can look at that, and when you put it on a mobile, you can just retarget it in that way, right? So I'll discuss one algorithm to do this, which is proposed by Shai Avidan of Tel Aviv University in 2007. So what I won't go to the code of it, but you have a very good code to replicate in this repo. They also have cool illustrations. You can check it out. So the seam the paper is called seam carving. It's from 2007. What it does is the following. So when you have an image, you can define an energy map of it. Energy map can be a gradient, or it can be the entropy values, or how close are the values. For example, let's say the entropy map is I mean the energy map is the gradient. For example, you take an image, you calculate the gradient, and then you want to calculate the following thing called as seams. What is seams is basically the minimum energy path you can I want to use my pointer. So the minimum energy path you want to take in order to reach from one border of the image to the other border of the image. So you can calculate it using for example Dijkstra's. You can just plot the whole image as, let's say a strip of an image of the graph, and you just find the shortest path between that end of the image and this end of the image, right? So then you get some minimum energy paths, and then you generate many such paths. So let's say for every point you generate such paths, and obviously you won't go through this man or this building because it's high energy. I mean it since the gradient is high there. So you don't want to mess with the gradients, but you want to remove the low energy paths, right? So when you generate these seams, to see here, they are the curves. So basically then you order all these curves based on their energy, like how much distance, basically distance, I mean the weighted distance according to what is in the pixel, and how much distance does this curve actually capture. And when you and just delete these curves and just replicate the pixels behind them. That's it. The algorithm is really simple, except I mean it can also be implemented efficiently using dynamic programming. And you can also do it greedily. Of course, you can just look at your neighbors and choose the least path that gives you there. Like, there are many methods, and you can do it very fast. And this can give, and by removing these red lines and joining the pixels, just by jamming them, you can get such a really nice retargeting results. Um, yeah. So this is a really cool technique, and this has been also extended to videos, and this can you can also retarget the videos along time axis. You can just calculate the gradient along time, and then you can get this seams along time, and then you can just delete whichever is the least important one. So another method which Alex taught in this class is basically this bidirectional similarity. So you want to minimize such an energy, which minimizes. You want to minimize such the energy as follows. Basically, you have energy of completeness and energy of coherence. What completeness means is, as shown in this image. I don't know if you can see the arrow properly. So this arrow points from source to target. This is source, X is source, and Y is target. And the arrow here basically points from target to source, right? So completeness means whatever is in your source should be in the target, and coherence means whatever is in the target it better be in the source. So you basically formulate an energy function with these both energies, and then you minimize it. And what he showed in the class is so basically you end up with such an algorithm. It's basically it involves two patch matches. So one is to find patch match between source and target. First you do patch match from here to here, and then here to here, and then you know how much importance do you give to completeness, how much importance do you give to coherence. For example, if you're doing inpainting, you shouldn't give importance to coherence, because you're obviously expecting something else that is to be placed in this black mark that you put in the image. So depending on the application, for example, in stereo you wouldn't want that. So for example, depending on the application, you can just give completeness versus coherence ratio, and then just calculate the weights accordingly. I have a pseudocode for it. So basically, you just until convergence, you just do from source to target to source, and you get two nearest neighbor fields, and then you go to the pixel that you want to reconstruct, and you calculate what is my pixel field in this point from S to T and T to S, and then you weigh them accordingly and take an average of them, and then for example, here let's say you want to decrease your aspect ratio by let's say this is your source. So there are some practical suggestions here. So when you want to do this, basically you get nearest neighbor fields from S to T and T to S, and then once you get these fields, you create a new image of 200 by 200, which is what you like, right? And you go to each pixel, and then you look at the field here and here, and then weigh them accordingly and put it here, and you do the same thing for the whole image like this. So this is so a couple of practical recommendations is which they proposed in the paper of PatchMatch is you can't just go from 250 to 256 to 200. You have to do it gradually to make sure that you end up with a good minima. Like they propose this approach as expectation maximization step, where expectation is basically you calculating the nearest neighbor fields, and maximization step is where you're computing this one, and you do it for and they propose to do it for 250. Let's say you're doing from 256 to 200. Don't do it directly. Do it from 256 to 230, and I mean go gradually instead of doing it directly. Right? That's very important. Otherwise, it will never converge. Otherwise, you're supposed to see a demo on this today. I never converged. So other cool thing that you can do is you can induce constraints on where you want to retarget the image. Basically, if you want this circle to be untouched, so you ask it. I mean, if you place a constraint like this, it will treat this whole thing as a different size circle, and it also helps the retargeting algorithm because it doesn't have to search at other places. It knows that this object is alone. You can treat it separately, and you can retarget it according to the dimensions you want the final image as. So it actually, instead of for the previous papers it was hurting them, but in this paper it was actually helping them because it is reducing the search space. For example, in sim carving, I don't think you can put constraints like this. If you want to resample this with sim carving, you have to. I don't know how you can do that, but it's very inherent in this method using PatchMatch to induce such constraints with bidirectional similarity, right? So yeah, so more thing I think I forgot to tell. Yeah, so I mean, you decrease from size from 256 to 230, and then you change your source to 230 and your target to something lesser than that, and then do it many times, right? So yeah, so in summary, basically, PatchMatch is a very powerful tool. I think it's used in many applications in Photoshop. Like it's been developed in Princeton, and Princeton is basically Photoshop, like Adobe. So they transfer the whole thing to Adobe, and it's used in Photoshop a lot. So it can run in real time when it's implemented appropriately. Like when you they also, I mean, you have some implementations which efficiently parallelize this patch match in a multi-threaded environment, and it can run in real time. And of course you can do many applications like one more thing I forgot. So since the algorithm is random, so you can, when you not whenever you it depends a lot on initialization, right? So whenever you initialize, it's not necessary that you will end up with the same result. So let's say yeah, so now that I want to fill this black patch above that is mentioned above, since the algorithm is inherently random, so once it decides to this is the actual image how it should look like. Once it decides to put patches from here, probably because it looked at this area and then it found the red pixel here, and then it propagated like this along these pixels, and like different trials will give you different patches. Since the algorithm is random, never it ended up with correct one. This is one negative example. Like you can also think of a scenario where you have I think wait you can also think of a scenario like this. This is from their presentation. Like you can when where you're given lot of images and a sunflower, and you just black out this region, so it doesn't know what to put there because it is so the it can synthesize many options that it can't. I mean, it can put a flower, it can put anything. It's essentially it minimizes the energy, right? So this is one thing. I hope I didn't forget anything. So yeah, it can be used in. It is used extensively in image and video retargeting algorithms, and yeah, and you can check out this the web page of to for code and stuff. Yeah. So any questions? Anything is not clear? Well, that's it. Thanks.